Okay, now there's a lot that lest you. Okay, this will work. That's good. Okay, so I know that there's for some of you that this class has gotten extremely concrete in a way that like you prefer it to be more theoretical. We are building the basic tool set for where things get theoretical out of this. Okay, so getting the residue theorem set up means that we're going to be able to do all the rest of it. So we're going to get right out the gate in the next quarter of this class with implications of the residue theorem and Laurent series. Okay. What else did I want to say? Oh yeah, how do you check? I can't believe I didn't actually, that you guys haven't seen this before. How do you calculate the order of a zero? It's a reasonable question to want to be able to know the answer to, given the number of poles of meromorphic functions that you're being asked to work with. So if I give you a function like f of z is equal to z to the third, it's pretty easy to calculate the order of the zero, right? There it is. It's got a zero when z is equal to 0, and it's order 3 because it has 3 factors of z sitting here. Now what you don't see when you look at that is that really this means that it's z to the third times 1, where this function 1 is an analytic function that's never equal to 0 anywhere, right? This is to say that f of z can be written as z to the third times g of z, where g of z is analytic at 1 and not equal to 0. Okay, so there's this sort of factor the term out way where you look at the power and you say, oh, it's order 3. Okay, so this is an order 3, 0.
Why does g of z have to be analytic at 1?
Because we're going to use the same thing for when we talk about meromorphic functions. It's analytic at 0. Sorry, yeah, analytic at 0. There's no, and basically you want to say this definition is going to be flexible enough that I can use it on meromorphic functions as well as just functions that are analytic, right? So I start with analytic function here, but really what I want is a function that is not 0 in a neighborhood of the 0 of the function. So I'm pointing out the extra fact that if I started with an analytic function, I retain an analytic function here. And it's order 3 because the power of z to the third, a z to the third factors out. Why do I have to put analytic here? Because if I factored out a z to the fourth, this function would not be analytic anymore. If I wrote f of z is equal to z to the fourth times 1 over z, this is not the way to compute the order of a 0 because you've now taken out 4 z's, yes, but the function you left behind is not analytic anymore. So you can get just the right number of z's out. The annoying thing is when a function is not just equal to some sort of polynomial, this is really annoying to do. So there's another way to do it. So I don't know if you guys you would have seen this maybe in a calculus class, but the idea is if you start taking derivatives of this thing, f prime of z is 3z squared, and f prime prime of z is 6z, and the third derivative of f is 6, and you evaluate all those derivatives at the 0 that you've identified, how many of the derivatives evaluate to 0? Well, the function is 0 at 0, and the first derivative is 0 at 0, and the second derivative is 0 at 0, and the third derivative is 6 at 0, which is not 0. But notice, that meant that the function and its first 2 derivatives were 0 when you plugged in. So the derivatives of a function actually keep track of the order of the 0 as well. So because I could take the function and 2 derivatives, and like when I evaluate at 0, the value remains 0, that's another way of calculating the order, a faster way of calculating the order. So if f has a 0 of order k at z is equal to z naught, if f fk at z naught, so the kth derivative of f is equal to 0, sorry, I should use a different letter here, if the nth derivative of f at 0 at z naught is equal to 0 for n running from 0 up to k minus 1, but the nth plus kth derivative of f of z naught is not 0. For function, first derivative, second derivative are equal to 0 when evaluated at 0, but the next derivative is not 0 when evaluated at 0. This looks trivial when you're dealing with polynomials, right? So let me give you something more complicated. What if I looked at a function like e to the z minus 1 divided by, maybe that's not so trivial. How about tangent of z divided by z cubed? Let's see if we can use this idea to pick out what the total order, so either this function has a 0 or a removable singularity or a pole at 0 here. So I'm going to assert that this function has a problem at z is equal to 0. Or maybe it's fine there. I don't know. Is tangent of 0 equal to 0? Okay, so tangent of 0 is equal to 0. So there's a 0 in the numerator at z is equal to 0. Is z a 0 for the denominator as well? Of order what? Okay, so the denominator, so there's a 0 in the denominator of order 3. How can I figure out the order of the 0 in the numerator? I could write the power series for tangent down, which I'm sure everybody in here just has memorized. Or you could derive it. And then, or you could take the series for sine and divide it by the series for cosine with polynomial long division, and then factor the right number of z's out of the thing. But those are not really elegant ways of figuring out, it's going to turn out to be 1, by the way, right? You do all that work and then the z factors out. But the idea here is I don't actually know if 0 is a pole or removable or a 0 for this function because I don't know the order of 0 that tan z carries with it. If this had order 3, then these would cancel completely and it would be removable. If it had order 5, then it would be a 0, it would be a removable singularity, but really secretly a 0 for the function. If it has order less than 3, then there'll be a pole there of some order. So I need to know what the order of the pole at 0 is for the tangent of z. How can I compute that? Well, f of z is equal to tangent z. It's certainly the case that f of 0, which is the tangent of 0, is equal to 0. So there is a 0 there. 0 is z is equal to 0 turns tangent into 0. Is it order 1, order 2, order 3? Without doing the power series, I could write down f prime of z, which is secant squared of z, and calculate the order of that thing, or plug 0 into that, and I get secant squared of 0. And I hope everybody in here remembers secant of 0 is equal to 1. Because it's just 1 over the cosine. Cosine of 0 is 0. So this is 1. Cosine of 0 is 1. Oh! How many of you guys have been in the class where I've told you about my old professor that's got the safety deposit box with the change of grades forms in it? Oh! Okay, so I have a professor that if you ever said on an exam that the cosine of 0 is equal to 0, he threatened us all that if we ever did that on a test, he would take all the points away from whatever you did on that question, and then it would also damage the questions around it too. So there would be like this nuclear explosion that would hurt the question above and below that one. Yeah, he also had I don't grade like that. He also had he was a great mentor. He was. He also said that he has a safety deposit. He's still alive, so for all I know, he's probably still there. He's got a safety deposit box with a bunch of change of grade forms in it. And in his will, there's a section that he showed us that says if he dies on anything that one of his students invented, that he retroactively gives them an F in any class that he taught them in. Things were different when I was a student here, I guess is the upshot. Anyway, cosine of 0 is 1. And so the secant squared of 0 is also 1. There's my tangent for the day. Okay, so what that says is, because the function was equal to 0, but the derivative is not, without computing anything about the series for tangent, right there, it has a 0 of order 1. Tangent has a 0 of order 1 because the function was 0, but the derivative wasn't. So tan z has a 0 of order 1. At z is equal to 0, which is very useful to be able to do without having to grind out an entire power series. And what it says is, now you know the order of the pole here as well, because you know if this has z is equal to 0 with order 1, and this has a 0 with z equals 0 of order 3, then in total it means that this has a pole of order 2. One of the zeros in the top, even if you don't do the algebraic cancellation, you still know that the total order of z is equal to 0 is 1 minus 3. Zeros minus poles, which is negative 2. So it's a pole of order 2. A Laurent series for this will have a term with a z to the minus 2 in it. This is, again, I'm trying to teach you guys some tricks to get around having to, if I don't ask you for a Laurent series, you could just do this if you want to. Okay, so that also kind of leaves open the question of, is there anything quick we can do with this? Because now the next obvious question is, okay, well, what if I asked you to compute the residue of this function? Doesn't that mean we have to compute a Laurent series? That's really irritating. So the next thing I'm going to show you is how to compute the residue without computing a Laurent series. So I'm going to write the theorem down, and then you're going to see that you already know it. Here's the theorem. How to compute residues without computing Laurent series. Someone remind me what a residue is. What is a residue?
Coefficient of the minus 1 term.
Yep. So the residue of f at z naught is equal to the coefficient of the z minus z naught to the negative 1 term in a Laurent series. So if you have a Laurent series, they're really easy, right? You just look at it, and there it is. It's just, if I write down 1 over z squared plus 6 over z plus the sum from n equals 0 to infinity of minus 1 to the n, z to the n. If you have a Laurent series for a function, here's f of z, then computing the residue is as easy as saying, oh, there it is right there. It's the coefficient of the 1 over z term. Yep.
If you don't have a 1 over z term, is the residue 0?
Yes.
It does not exist. Okay.
Yeah, so it's possible that there could be a 1 over z squared here, but not a, yeah. So in that case, there is no residue. Yeah.
But there is no residue or it's 0?
Well, you would say like that means the same thing, right? To say that there is no residue is to say that the residue is 0 there. So in this case, the residue of f at 0 would be 6. Okay. So the other way that you can compute a Laurent series is like this. Suppose f has a pole. This does not work for essential singularities. It works for poles. It's a good thing that most engineers only work with rational functions. Suppose f, you wouldn't want to design a system with an essential singularity in any way. Suppose f has a pole of order k at z is equal to z naught. Then, the residue of f at z naught can be calculated by doing 1 over k minus 1 factorial times the limit as z goes to z naught of the k minus 1th derivative. This looks more confusing than it is, I promise. Times z minus z naught to the k f of z. This is a computational formula for the residue. But it just involves limits. Okay, now somebody impress me and tell me, other than Madeline, who was in my office and saw this earlier. Somebody, although you could impress me if you can explain what's going on here. You're welcome to. But anybody else as well. What is going on with this? What are we really doing secretly? Because it looks like some magic spell that I cast on the function. But remember, f is analytic except for at the singularity. And so secretly in the background, if there's a pole of order k, it means there's a Laurent series running around in the background. Even if I didn't find it, it's still there. Yep? This is the k minus 1th derivative. So d by dz. So this symbol dk minus 1 over dz to the k minus 1 means the k minus 1th derivative. Not Donkey Kong. Yep. You take the product, and then after you take the product, you take all these derivatives. Okay, it's going to be totally obvious what's going on when I write down what's actually happening. So this looks like a mystery until you think about what this would actually do to a Laurent series. So let's actually just write a Laurent series down, like 1 over z squared plus 1 over z plus 1 plus z squared plus z cubed, and so on. So this has a pole of order 2 at 0. How can I use calculus to figure out this number without actually writing the Laurent series down? Well, what does the formula say to do? If z has a pole of order 2, I'm supposed to take all of this and multiply it by z squared. That's step 1. Is we're going to compute z squared times 1 over z squared plus 1 over z plus 1 plus z and so on, which is 1 plus z squared plus z to the third. Maybe we'll make this fancy and put a pi up here so we can keep track of where that is. So this is a pi, and now there's a pi right here. I mean, the idea is I'm just trying to keep track of where the one thing I'm looking for happens to be. Notice that what the z squared did is it got rid of all the negative power terms. Okay. All right, step 2. We're going to take some derivatives. How many derivatives? Well, what I'm trying to do is I'm trying to slide that pi that I'm looking for over so it's the constant term. Right? So I'm sort of shifting the function over. And how do I do that? Well, if I take derivatives, the powers of these are going to go, they're going to disappear, right? I'm going to keep taking derivatives, and eventually all those z's that are less than this are going to disappear. So this has how many derivatives to take? 1 derivative. So we compute d by dz of 1 plus pi z plus z squared plus z cubed and so on. And we get pi plus 2z plus 3z squared and so on. So the derivative step just shifts the residue over to be in the constant spot. And we do just enough derivatives so that wherever this thing started, it lands in the constant spot. Then we take a limit as z goes to z naught. Well, what does that do? That kills off every other term that survived. Since we're taking a limit now, step 3, take a limit as z goes to 0 of this, and all of these guys go away. So what comes out of this is pi, really secretly pi times 1, because that was the power that came down from the exponent, right? This has a z to the first, and the 1 came out front. And what does step 4 do? Step 4 just accounts for the fact that you took a bunch of derivatives, which meant you kept dropping the powers of the z to the k out front, and you need to eliminate them. So step 4, you multiply by 1 over 1 factorial times 1 times pi, which eliminates the 1's, and gets you the residue pi out the other side. And the point is, you can do this computation without having any reference to the Laurent series. You don't need this to do this. This would have worked for any f that I knew that had this structure. Yep.
Why don't never mind, I answered my question.
What was the question?
I was going to say, why can't you just multiply by 1 over z to get pi alone?
But you would need to know the Laurent series to do that, right?
Well,
Oh no, because the step where you eliminate all the other terms doesn't work, right?
Yeah.
That's the issue.
Yeah, that's what I realized.
Yeah, so basically we're tricking it to be a Taylor series, and then we're sliding it with derivatives to get the thing we want in the constant spot, possibly multiplied by a bunch of powers of z. Okay. Does that reveal what's going on here, or do you want to see me do it again with a more complicated function? Yep.
Does it work for like non-polynomial?
Yes. In fact, let's do it. So I'm going to write one down. Let's actually compute the residue of this function. So we can compute the residue of this function without knowing anything about what the Laurent series of this thing is. I could do this with the Laurent series. I could write down the Laurent series for tangent and then divide everything by z cubed and then go looking for the z to the minus 1 term. In fact, we did that. And you guys remember we had that thing where you were sitting in here working on the tangent and it sucked because the power series for the tangent is something nobody remembers. It's not a regular pattern. I mean, it is, but it's terrible. So let's compute the residue of this thing. What do I need to know in order to compute the residue using this formula? The order of the pole. Fortunately, we have the order of the pole. So this technique for evaluating the order of the pole opens the door to using this without computing the Laurent series. So here's our question. What is the residue of the function tangent of z over z cubed at 0? Yes, it's the coefficient of the z to the minus 1 term in a Laurent series, but I don't want to compute it. So instead, I'm going to say, okay, the order of z is equal to 0 as a pole is 2. So what the formula says is it should be equal to 1 over 2 minus 1 factorial times the limit as z goes to 0 of the first derivative of z squared times tangent z over z cubed. If I can do that computation, I'll have the residue. And that's just like a calculus 1 exercise. Calculus, whatever, 3, because maybe you need Laurent's, or L'Hopital's rule, maybe. Okay, so you put the z squared in there because whatever the Laurent series is, this would shift the residue to the constant spot. So that gets you, so step 1 says we're going to do z squared times tangent z over z cubed, which is tangent z over z. Step 2 says that I'm supposed to take that derivative of that thing, 2 d by dz of tangent z over z squared over z, sorry, just z, is equal to, oh man, really? Secant squared z with a z in front of it minus tangent z all over z squared, because you got to use the quotient rule. Still better than Laurent series, I promise. Step 3. Step 3 says I'm supposed to calculate the limit. So now I'm going to take the limit as z goes to 0 of z secant squared z, not secant squared z. Did I do the derivative wrong, by the way? Or am I right? All right. Unfortunately. Z, and in the denominator is z squared. Okay, so I got to keep L'Hopital's rule in my back pocket here. So what do I get on the top? I have a 0 minus 0, which is 0 divided by 0. Okay, so by L'Hopital's rule,
I thought we weren't supposed to do that in this class.
we can now. The reason that we can is this limit is guaranteed to exist. And when a limit is guaranteed to exist, then it must agree with the limit when you take it along the real axis. So by theorem, this limit exists. Yep.
Why does this limit have to exist?
Because that's what this is a theorem, this method of computing the residue. The residue will either be 0. So if you have a Laurent series and you have a pole of order k, then that means that z to the minus 1 term is in there. It may be a 0 on top, it may not be, it may be a non-zero on top, but it's there. So this process is not a void process. It will be guaranteed to produce something that has a limit. So analyticity forces this limit to exist. And yeah, I'm going to write L'Hopital, but really secretly what you should think is I'm using it because I know going in the limit exists, which means I can think of myself as coming in on the real line, and the limit on the real line must agree with the complex limit. So I can use real tools, basically, is the idea.
We can take a secondary class.
We're going to have to. It's just L'Hopital's rule. Come on, it's not like we're going to quotient rule this thing. You guys know how to take L'Hopital's rule. I mean, so you take the derivative of the top, which is 1 times secant squared z plus 2z secant z times the secant of z times the tangent of z minus the secant squared of z, all divided by 2z. Well, then let's check. Maybe we got lucky. Maybe we got lucky. Oh shit, there's a 0. Oops, I shouldn't have sworn. Oh, but look, the secant squareds cancel. Oh, but then there's an extra secant squared and a tangent. Oh man. Okay. So let's actually reduce this slightly. So there's a secant squared right here and a secant squared right here, right? So we get 2. Really? Secant squared. I'm sorry, Madeline, I did this wrong in the office earlier. Well, then why didn't you say something?
I realized it like 10 minutes later.
Oh, wait, we can just cancel.
You were done.
Yeah, this is fine now.
Oh.
No. 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 This can't be what it is. Because then I get 0 as the...
It's true.
Wait, hold on. Z. Is it true? Oh, it's all even terms on the bottom. It is 0, isn't it? Yeah, okay. Yeah. No, I'm right. I thought I was wrong, but I'm actually right. Okay. So, this is equal, so the limit is Z. That was another thing that old bastard used to say was like, I made a mistake once. I thought I was wrong. That was one of his favorite sayings. So, the limit as Z goes to 0 of secant squared Z tangent Z, which is 0. And if you check in the Laurent series, what you'll see what's happening is this has odd powers. And so if you divide a bunch of things with odd powers by something with odd powers, you can only get even powers out the other side. So there can't be a -1 term. So the residue being equal to 0 is what you expect to happen. Okay, now I know this looks long-winded, but really we turned a hard problem from complex analysis where we had to find this Laurent series into a derivative. Oh, you have to remember the quotient rule and L'Hopital's rule. So it's way faster to do this. Now I want you to imagine if this had been buried inside of an integral, here's the problem you are now in position to solve. So we're building this up into an exam problem. We're working backwards. We're starting with an easy idea and building it backwards into an exam problem. Now what's wrong? Is it right?
Yeah.
Okay. I'm not saying now what's wrong because I'm mad at anybody except myself for like being incapable of doing calculus. I'm teaching calculus 3 right now. Anyway, so now let's reverse ourselves. We've reverse engineered ourselves into an exam question that looks really hard. The integral around the circle modulus of z is equal to 1 of the tangent of z over z cubed dz. And that's what it's going to be. It's going to be 0. It's going to be 0 because we know the residue, right? 2 pi I times the residue. We learned that this thing is equal to 2 pi I times the residue of f at the one singularity that lives inside. One singularity of that function. It only has one singularity, and that singularity is inside the curve. We have the circle z is equal to 1. We have a singularity sitting on the inside right there at z is equal to 0. The one singularity theorem says that this integral is equal to 2 pi I times the residue of the function at that point. And that means it's 0.
And if there's more than one singularity, we can't use that theorem.
Ah, you have just anticipated the actual residue theorem. So I'm using this to back end my way into the residue theorem. Okay, so this right here, this idea where we use the derivative to find the order of zeros, and then we can calculate the order of a pole, and we can use this computation to calculate the residues, makes using the one singularity theorem really easy. Unless your professor says don't use that. Okay. So here's what the residue theorem says. I'm going to draw a picture and you're going to tell me what the residue theorem says. This is a picture of the one singularity theorem. Suppose that f has a singularity, f has a pole at z is equal to z naught. What did we do? We said that, we can actually reduce it to this. We drew this little contour around it, and then we said, the integral around this curve is the same as the integral around that little circle, but the integral around that little circle was equal to the residue of f at that point, right? That the integral of f on the big curve, dz, was equal to the integral of f around that little tiny curve that's around C0, which was 2 pi I times the residue of f at z naught. What if I put two singularities inside? Well, there's a Cauchy theorem, right? The Cauchy theorem and the circle contour theorem says that if there were two singularities on the inside, is there anything from stopping me from doing this? So the integral around C of f of z dz is equal to the integral around that little circle that goes around z naught plus the integral of f around that little circle that goes around z1. And what's that equal to? By the one singularity theorem. 2 pi I times the residue of, so this one is 2 pi I times the residue of f at z naught. And what's that one equal to? 2 pi I times the residue of f at z1. Or, if you like, 2 pi I times the sum of the residues of f at zi, where I runs from 1 to 2. Can you imagine a way that we could extend this theorem if there were more singularities on the inside?
No.
I know, it's pretty hard to imagine. So what the residue theorem says is, and this is sort of the baby version of the residue theorem. So we'll call this residue theorem V1, or baby residue theorem.
You're gonna get one of these three theorems?
Well, I have to teach you what winding number is to teach you like the beefier version. And that winding number takes that's non-concrete, and it takes more time to talk about. So I'll be able to talk about that. I will have time to talk about that, but I can't talk about. I'm trying to make this really concrete. Like today's lecture is supposed to be, let's take all the pieces and glue them together into a technique that we can use. So the baby residue theorem says that if you have f, and f is analytic inside and across a simple closed contour, C, except for a finite number of poles. We don't use poles. A finite number of singularities. Z1 up to Z capital N. Then it's just this idea. We're going to say if there's n things in here instead of two things inside here, then the integral of f around C is equal to 2 pi I times the sum of the residues of f at all of the singularities. It's just that theorem with more points in it. Yep.
They need to be isolated or not?
So if there's a finite number of them, they have to be isolated. So, it's a good observation, right? So we can say a finite number of. It's redundant to say it, but it's important to point out these are isolated singularities. So the point is, the only way you can get a non-isolated singularity would be if you took a function and you say, here's the worst analytic function I can, or like meromorphic function I can think of. So why don't you let fk be equal to 1 over z minus 1 over k. Now that function has a singularity at 1 over k, right? What am I going to do with these to make a really bad function?
Sum them up.
No, worse than that. I'm going to multiply them. So now to find a function f of z to be equal to the product from k is equal to 1 to infinity of these little fk's. And in that case, if you have an infinite number of singularities, what's happening is you have this sequence of singularities that's each one of these singularities themselves are isolated, but they're approaching some cluster point. That can only happen if you have an infinite number of them. That's really, and a branch point is different than a singularity is the other like important topic there. These are terrible. I mean, by terrible I mean these are awesome. Awesome. Infinite products of things is. If you've never seen infinite product notation before, I have such things to show you. Anyway, Yep.
What do you do if you have just a completely like discontinuous interior?
What do you mean?
Your function analytic nowhere on the interior.
Inside and across a simple closed contour except for a finite number of points.
No.
Basically,
I get that. I'm asking you, like, what happens?
oh, all hell breaks loose.
Okay.
I mean, the basic idea is just because you can evaluate a function on a contour doesn't mean you can actually do anything with it, right? So suppose you have a hot mess. So here you go. There's a hot mess right there. Right, and then you've got some like oasis of stability out here, right? So oasis of stability. Now, certainly, it's the case that you could evaluate this thing parametrically because the function is well defined and analytic on this curve C right here, right? I mean, integrate around a hot mess. It's up to you, I suppose. But like the point is that none of this theory works on something like this, right? If it's really like totally discontinuous and awful on a region like this, all of this theory breaks down because that relationship between the boundary behavior of the function and the interior behavior completely falls apart. And in this sort of case, you have a couple of options, but most of them are do it numerically with parametric integral and like stare in horror at what comes out the other side, and also reformulate your system so you're not doing this. Yep.
When you sum the residues, don't you have to take into account the direction that your contour goes around the singularity?
So this is why I say it's a finite number. It's a simple closed contour in this case. So yes, you do. I mean, simple closed contour C oriented positively. So yeah, this is the most basic picture, which is this. We have a simple closed contour. It's got a finite number of points in the interior, Z1, Z2, and Z3. The orientation is correct. And all we're really doing is, it's a two-step thing. We're saying, oh, really secretly all the residue theorem says is, that contour is the same as these three. And the integral on each of these, the one singularity theorem applies to. So it's 2 pi I residue, 2 pi I residue, 2 pi I residue. Yep.
Just tiny. I don't know if it was related to what Max was asking about, but that negative sign should be like in front of both those integrals, right?
What negative sign?
Under the f of c closed contour of c dz is equal to.
This?
Yeah, should that be on both?
This is an equal sign.
There we go.
Thanks for, yeah, that's just a terrible equal sign. It's not a minus. Otherwise, there's not even an equation. It would be equal to 0 by the Cauchy theorem, right? But the idea of, like, what are the two big thematic ideas we're bringing together here? Big contour integrals reduced to piles of little ones. The little integrals are easy to compute with using the residue, or the Cauchy integral theorem, if you like. Because remember, the Cauchy integral theorem really secretly is what the residue theorem is doing, right? Cauchy theorem lets you take this and reduce it to these. These are easy to compute with knowing that Laurent series exist for these functions. And then you just apply the residue theorem, or the one singularity theorem over and over again. So all this really is the Cauchy integral theorem all like gussied up with bells and whistles. But that's what it is the Cauchy integral theorem. So it's a fancy way of just recording what the Cauchy integral theorem would tell you if you did it by hand. And you should recall that you've done a bunch of these by hand already, where you take the function and isolate all the singularities and reduce it to 3 integrals and then compute them all separately and then add them up. You've been doing this the entire class since we introduced integration, just not in this sort of combined language. Okay, so now an obvious question is, I keep talking about winding number and this question of orientation. What happens if the curve is more complicated? So I'm just going to indicate a little bit about what happens, like where we can get the real, what I would call like not the non-baby residue theorem. And the idea there is that if you started with a function, say that had 2 singularities, and then I wrap some curve around them. So I take some C that looks like this. This is a contour C, and you can trace it. So it goes up this way, and then it goes down here, and then it goes this way, and then it comes back around like, did I even make it match up? It goes, what the hell did I do? Oh, sorry. It goes like this, up, and then around like this, and then through this way, and up like this, and then down here. So that's you can integrate around that contour. You know, in theory, you could parameterize that thing. And the question becomes, what does the residue theorem look like in this case? And the idea is you can take this curve and think about it as decomposing into circles like that, but there may be more than one circle around each point. How many times does the curve wind around the point Z2? Well, there's a complete, if any of you have seen topology before, you may have seen this trick. You start at the point and you write a ray that goes from the point out to the unbounded set. And then you count the number of times the curve is crossed.
In the same direction.
In the same direction. +1 for everything in the counterclockwise direction, -1 for everything in the opposite direction. So the curve, we should say C goes around Z2 twice. And that's called the index of the curve around Z2, or the winding number of the curve around Z2. The curve has wrapped around the point Z2 twice. There's 2 loops of it that are out here that you can't get rid of no matter how you slide this curve around and no matter how nice you make it. It will always twist around Z2 twice. This point, it wraps around twice but in the wrong way. So the index this direction, so here we're going clockwise around Z2. I picked a ray, I counted the number of times it went through. Around this one, the index or winding number is -2 because it wraps through twice but in the backwards direction. And so in that case, what the residue theorem would say is, it's still true, but you say it's the residue at Z2 times the number of times you wrapped around, plus the residue at Z1 times the number of times you wrapped around. So the integral here would be -2 times the residue at Z1 plus +2 times the residue at Z2. So the full theorem has this sort of topological thing going on where you have to keep track of what the curve is doing around the points as well. And I just don't want to formally put that down yet, exactly what that means. Right, the formal definition of this. But this is how you get the full theorem out, where instead of just residue f zi, there's this extra bit that keeps track of the index, or the winding number of the curve around the points too. Yep?
The prior result that we showed from tangent over CQ, also, like minus the limit part, would that also hold for sine?
Yes. And that one you can show directly. You can go in there and if you took sine, which is z minus z cubed, and then you divided it by z cubed, you get 1 over z squared.
Oh, just that, right?
Yeah, you're going to get 1 over z squared and then nothing, and then just a constant, right? There's nothing left there, which means that there's no residue term, so there's no residue. All right, so this is like next time what we'll do.